Hi everyone, I am Santhi from Department of Mathematics and Statistics, Bhavan Vivekananda College. I am here with my lesson 23 in linear algebra on vector spaces. In this lesson, I am going to explain about linear transformation or vector space homomorphism. In your previous classes, you would have learnt in groups about homomorphism of groups the same way for rings, homomorphism of rings, which are mappings in between any two groups or rings satisfying given some conditions. Now you are learning about vector spaces. Now and then this linear transformation is nothing but a mapping between any two vector spaces satisfying given conditions. Let us define linear transformation. Let V and W be any two vector spaces as shown here in the diagram. V and W are any two vector spaces. Then a linear transformation T from V to W is a rule or mapping which assigns to each x in V, here x is in the domain V, a vector t of x in W. So there is a vector t of x in W such that it satisfies the following two conditions. What are the two conditions? First condition is t of u plus v is equal to t of u plus t of v for all vectors u and v belong to V. And the second one, t of c into u is equal to c into t of u for all scalars c and for all vector u belong to V. Now let us look into it in detail. So look at the diagram. You are given here two vector spaces V and W. Then T is a mapping from V to W, then which is assigning for every x in the domain there is a T of x in the codomain. So this basically T is a mapping from V to W. Now, then when will it be called as a linear transformation? When it satisfies two conditions. First condition is regarding vector addition T of u plus v, and the second condition is regarding the scalar multiplication, because these two are the operations which are important on vector space. So here I take two vectors u and v from the domain. Whenever u is there, I will have t of u here. Whenever v is there, I will have t of v here. Now, when there are two vectors u and v in V, their summation u plus v will be also there in V. Now, whenever u plus v is there, t of u plus v also will be there in W. Fine. Now, I have t of u, I have t of v. Then what is the summation of t of u and t of v? T of u plus t of v. This will be also there in W. Now, what is our first condition? T of u plus v is equal to T of u plus T of v. So, whatever this T of u plus v, which is the image of u plus v, should be equal to T of u plus T of v. That is the first condition. Now, what is the second condition? Take a scalar c, then c into u is a vector, will be also there in V. So, Cu will be there in V. Then, whenever Cu is there, its image T of Cu will be there in W. Fine. Now, T of U is there in W. Then take a scalar and multiply T of U with C. Then it is C into T of U, that is also there in W. Now, our second condition is T of C into U is equal to C into T of U. Right. So, if these two conditions are satisfied, so this is our condition 1 and this is our condition 2. If these two conditions are satisfied, then we call that mapping as a linear transformation. Let us try to understand linear transformation by this example. So, this is given here. Define T from P2 to R2 by T of P is equal to a column vector P of 0, P of 1. Then show that T is a linear transformation. So whenever we are doing a linear transformation problem, so first we have to be knowing what is a domain and what is a codomain. So T is a transformation from P2 to R2. So first let us write what is P2. P2 is equal to all polynomials, set of all polynomials up to maximum degree 2. So it will have polynomials of the form P of T. How is this P of T? It is a second degree, maximum second degree polynomial, Ct square, where A, B, C are real numbers. This is P2. Now let us see what is R2. What is R2? R2 has all column vectors with two rows x, y such that x comma y belong to R. Now you have the mapping between P2 and R2. So this is P2 and this is R2, and here you have polynomial P of T, and here you have a 2 by 2 matrix xy. So this is mapped to not xy. Let me change this. So this P of T is mapped to, what is it given here? T of P is equal to P of 0, P of 1. So this is P of 0, P of 1. This is what the transformation T you have. Now we have to prove that this is a linear transformation. So for linear transformation, what do we have to prove? We have to prove two conditions. We have this. This is a definition. T from V to W is a linear transformation if number 1, T of U plus V is equal to T of U plus T of V, and then number 2, T of Cu is equal to C into T of U. This is what we will prove for any a transformation to be a linear transformation definition. So we have where are these U and V are taken from? Where U comma V. So I can write here U comma V belong to the domain V and C is a scalar. Right. So what is the domain here? Domain is P2. So we should take two elements from P2. So I'll take let U comma V belong to P2. So that is, let me take U is equal to P of T. In what form it is in? Let me take it as A1 plus B1T plus C1T square. And V is equal to Q of T, which is A2 plus B2T plus C2T square. Where are these? They are in P2. Then what will be U plus V then? Implies their summation U plus V, because you want to add T of U plus V. So how do you add polynomials? It will be, so it is nothing but P plus Q of T, which is given by A1 plus B1 plus, it's not A1 plus B1, it is A1 plus A2 plus B1 plus B2 into T plus C1 plus C2 into T square. C1 plus C2 into T square. And also, what is C into U means? That is C into P of T, that is equal to C into, let me write CA1 plus CB1T plus C1T square. This is. Now let us consider what is first point I will prove. Consider T of U plus V is equal to. What is meant by T of U plus V for us? It is T of P plus Q of T. Now by definition, What is T of P plus Q? It is given here. The definition is given. T of P is P of 0, column vector P of 0, P of 1. So I will write here we have T of P means P of 0, P of 1. Now what will be T of P plus Q of T then? In that case it will be P plus Q of 0 and P plus Q of 1. What do you mean by this? In place of T, write 0. In place of T, write 1. So this will be equal to, what is P plus Q of T? A1 plus A2 plus B1 plus B2 into 0 plus C1 plus C2 into T square. T square means here it is 0 square. And then what is P plus Q of 1 means it is A1 plus A2 plus B1 plus B2 into 1 plus C1 plus C2 into 1 square. This is a matrix. Here this is a polynomial, but the transformation is giving us a matrix. So this is equal to, this is 0 and this is 0, so it is only A1 plus A2, and this will be A1 plus A2 plus B1 plus B2 plus C1 plus C2. This is LHS. So you have to prove that T of U plus V is equal to T of U plus T of V. So I just found T of U plus V. So this is LHS. Then I will consider now T of U plus T of V is equal to, that is T of P of T plus T of Q of T. Now by definition, what is T of P of T? By definition, T of P of T is nothing but T of P is equal to column matrix P of 0, P of 1. So here if I apply that, T of P of T is equal to, it is P of 0, P of 1 plus Q of 0, Q of 1. This is equal to, what is P of 0? So in the polynomial P of T, that is A1 plus B1, A1 plus B1 into 0 plus C1 into 0 square. Then again P of 1 means A1 plus B1 into 1 plus C1 into 1 square plus, now this second Q of 0 means A2 plus B2 into 0 plus C2 into 0 square, and then A2 plus B2 into 1 plus C2 into 1 square. This is equal to, here you have A1, here you have A1 plus B1 plus C1, plus here you have A2 and A2 plus B2 plus C2, which is nothing but A1 plus A2, A1 plus A2 plus B1 plus B2 plus C1 plus C2. This is RHS, and we can observe here whatever you got LHS, this is LHS. These both are the same. Therefore, LHS is equal to RHS, that is T of U plus V is equal to T of U plus T of V. Now we have to prove the second one. What is there in the second one? So let C be any scalar. We have to take some scalar. Any scalar. Then to prove that, we have to prove that T of C into P of T is equal to C into T of P of T. This is what we have to prove. So C be any scalar. What is C into P of T? Equal to C into A1 plus B1T plus B2 C1 T square. That is equal to CA1 plus CB1T plus C1T square. Now what is T of C of P of T? By definition, it should be a column matrix where you will write C into P of 0, C into P of 1. So this is equal to C into P of 0 means A1 plus B1 into 0 plus C1 into 0 square, and A1 plus B1 into 1 plus C1 into 1 square, which is equal to C into A1 and then A1 plus B1 plus C1. So this is nothing but C into P of T. Therefore, T of C of P of T is equal to C into, this is this one is T of P of T. So it is equal to C into T of P of T. Hence, by these two conditions, we can say that T is a linear transformation.